In this screencast, we are going to talk about measurements and significant figures. Now, in the United States, for measurement, we use the English system. In the English system, we use things like inches, a foot, miles, those types of things. When we talk about these are our units, and the unit is just the basic quantity of mass, volume, or whatever is being measured. Now, every measurement that you make will have a number and a unit. So there'll be two parts to every measurement. So a measurement is really useless without its unit. Now, the English system that we talked about that we use is also used in two other countries. It's used in Myanmar and it's used in Liberia. And you can see those countries here and here, as well as the US. It's just, when we talk about this English system, it's just really a collection of functionally unrelated units. So it's something along the lines, as I mentioned, of, there's 1 foot equals 12 inches, right? So it's quite a bit to remember. Most countries and scientists use the metric system. When we talk about the metric system, right, this is composed of a set of units that are related to each other using powers of 10. So it's composed of a set of units that are related to each other by powers of 10. And so when we talk about this, there are two parts to the metric system unit. There is a base unit, and then there may or may not be a prefix, right? So, for example, that base unit would be a meter. And then we can, because meters tell us about distance, and then we can use a kilo, hecta, deca, deci, centa, milli as the prefix, and all of those are related by powers of 10. The front and part, that prefix, helps us with the size, right? So it helps us make the numbers more manageable. Let's look at the base units of the metric system. Now, the base units of the metric system, right, when we talk about mass, this is the quantity of matter in an object. It's not synonymous with weight. And the standard unit is a gram. This has kilograms on it, but the standard unit that we're going to consider is just the gram. Length, right, is the distance between 2 points. Meter is the standard unit. Volume is not on here, but that's the space that's occupied by an object, and that standard unit is a liter. And we're going to talk about that a little bit more later. Time is seconds. Temperature is Kelvin. The amount of a substance is a mole. Electric current is ampere, and then luminous intensity is candela. So these are our base units. Now, let's talk about those prefixes, the things that go in front. This is a list of prefixes. Now, there are more than this. These are the most common ones. Where we have mega with a large M, and that equivalent is like a million. We have kilo, and that's like saying 1,000. So if you have 1 kilometer, that's like 1,000 meters. 1 megameter, that's like 1,000,000 meters. We have deca, which is like 10. So 1 decameter is like 10. Then deci, centa, milli, micro, which is this upside down U, and then nano. We'll talk more about these in our next screencast as we convert between the two units, and of course we'll do some problems in class. Let's talk about volume for just a second. Volume is a derived unit. When we say derived unit, basically we get to a derived unit by saying, hey look, it is multiplied, or you have these multiplied or divided units. That arrive at a new unit. Well, what do I mean by this? When we think about volume, for example, volume is measured in liters, right? With a L as the unit there. And a liter is a cube. So we have a cube here. And when we talk about this, it's a decimeter on each side. So if we look at there being a decimeter on each side, to get to volume, it would be 1 decimeter times 1 decimeter times 1 decimeter equals 1 liter. That's the volume. So we take the length and the width and the height. A milliliter is a centimeter cubed. So 1 milliliter equals 1 centimeter cubed. I just want to remind you, when we multiply 2 units, they're squared. When we multiply 3 units, that's where we get the cube from. So this is a really common measurement that we'll see. You will also see this where 1 milliliter equals 1 centimeter cubed, which equals 1 cc. We see that on a syringe, and it's pretty common when we give medicine. Now, sometimes when we work in science, we have these very large numbers or these very small numbers, and to help make these more manageable, we use scientific notation. Now, you have probably worked with scientific notation before. These represent a number as a power of 10. So this, we're just going to dust off some brain cells and review it for just a moment. So, for example, if you have 4,300 and you wanted to put that in scientific notation, you would take the decimal and you'd move it over 1, 2, 3, where it's between the largest number and then the number that's next to it. So it's right after that largest number. When we put this into scientific notation, it's 4.3 times 10 to the third, because there's 1, 2, 3 jumps of the decimal we've done. That's a large number, and you'll notice the exponent here is a positive number. When we look at a very small number, like this number, we do the same jump, 1, 2, 3, 4, 5. You're going to jump to where you get to the first non-zero number. So you want to be right after that first non-zero number. That gives us 9.72 times 10 to the negative fifth, because we jumped 1, 2, 3, 4, 5. Now, because this is a smaller number, that's where we have the negative there. So for larger numbers, with the exponent will not have a negative in front of it, it'll be positive. For smaller numbers, it'll be negative. Now, when we make measurements in the lab, there's always uncertainty that's associated with the measurement. A digit, and so because there's uncertainty that's associated with this, we estimate a digit after the division. So the division's on the measuring tool. So what do I mean by this? If we look at this measuring tool and we're trying to measure this piece of wood here, we see that we have a division at 4 and a division at 5, but it's not really on 4 and it's not really on 5. So what we do is we estimate it right here in between. So when I look at this measurement, I may say, okay, hey look, that looks like 4.4 centimeters. But you may say, no, Dr. Pierce, that's 4.6 centimeters. And someone else may say, no, that's 4.5 centimeters. And all of these are right. And this digit here, the one where we don't have a mark, right, because it's we're trying to figure out kind of where we are right in here. That is our estimated digit, right? And that we refer to a lot of times as the uncertain digit. Okay. A measurement will always have some degree of uncertainty. So, for example, right, we can see that that piece of wood comes right there between 4.5 and 4.6. So you may say that's 4.55 centimeters. I may say it's 4.57 centimeters, right? Both of those would be correct, with that 5 and that 7 being the estimated digit. A really common question is what happens if that wood, if we're measuring, is right on that 3? Well, you still have to have an estimated digit. It's just that estimated digit is going to end up being 0 there, okay? The really important thing to understand is that these numbers, with our certain number here, that number is reflected as a spot on our measuring tool. And then our estimated number, these are significant. They can tell us, without looking at the measurement tool, how specific the measuring tool is. And so we describe those digits as significant figures. So significant figures are all the digits in a number representing data or results that are known with certainty. Plus one uncertain digit. So that uncertain digit is our estimated digit. So significant figures, which I'm going to abbreviate as SF. So SF is significant figures, right? These help us determine how specific the measuring tool is without viewing the tool. Okay. So we have some rules that help us with significant figures, and these are rules that all scientists follow to help us or to let us know that the numbers that we're looking at reflect the measurement tool and how specific that measurement tool is. So let's look at those significant figure rules. Significant figures, right? When we talk about these rules, right? All non-zero numbers are significant. So zeros are a problem, and zeros, it just depends on the location. So what do I mean by that? Leading zeros are really what we call a lot of times placeholders. These are not significant. Right? We can also have trailing zeros that are placeholders. These are also not significant. And so we're going to look at some examples of this. The other thing that's not significant is exact numbers and conversions. These are not significant. So exact numbers are things like, oh, there's 32 students in a room. They're counted numbers. There's 12 eggs in a dozen. Those types of things. And so we just ignore them when it comes to significant figures. Let's look at some examples of this. So all non-zero integers are always significant. So when we look here, these are all non-zeros There are 4 numbers there. That means there are 4 significant figures. My suggestion would be to pause this screencast and try to determine how many significant figures are here, and then restart the screencast so you can see the answer. There are 3 significant figures there. I mentioned before that leading zeros are not significant. When we talk about those leading zeros, we refer to them as placeholders. Placeholders just represent or help us know how big or small the number is. Leading zeros like this, we ignore. So we ignore these until we get to a number. So there's 1, 2, 3 significant figures there. Again, you can pause the screencast and try the next one on your own. So when we look at the next one, we ignore all of these numbers and we start here, where there are 4 significant figures. Now, trailing zeros are not significant unless they come after a decimal point. So you have to look for the decimal point. This does not have a decimal point, so these are also just placeholders. So that means here, there are only 2 significant figures, the 2 non-zero numbers. When there is a decimal there, that makes anything that comes after it significant. So these 2 zeros are in fact significant, and there are 5 significant figures there. Captive zeros come between 2 non-zero numbers. They are also always significant, so there are 4 significant figures here, and there are 5 significant figures here. When we do this, if you see scientific notation like 3.920 times 10 to the 4th meters, any number in scientific notation is significant. So any number shown in scientific notation is significant. So this would have 4 significant figures here. Now, when we do math in science, the number that we get after we do math can't be more specific than our least specific measuring tool. And so we have some rules that help us with this. So before we get to the rules, it helps to review some rounding rules really quick. You will end up having to round. This helps us drop insignificant digits, and you only do this at the end of the calculation. So if the number is 4 or less, you stay, right? And let's say the next number, if the next number is 5 or more, you round up. So let's look at some examples. If I need to round to 3 significant figures, so let's say the problem said round to 3 significant figures, and I have this number, 57.54. That's 4 significant figures. I need to only have 3 significant figures in the answer. I would look at this number here and I would say, hey, look, it's 4 or less. So we stay, we don't do anything to this 5. So that would be 57.5. Let's say that I had 57.55. Okay. When we look at this, right, this 5 falls into this category where it's 5 or more. So we need to round up. That means the number that's next to it needs to go up to 6. So that answer there would be 57.6. So this is an example of rounding. Now, as I mentioned before, the number of significant figures in the final result cannot be greater than the weakest link used in the calculation. The weakest link is just the one with the least amount of significant figures or the least amount of decimal places. The actual rule depends on the mathematical operation. So let's look at multiplication and division first. When we talk about multiplication and division, we need to look at the number of significant figures that are in each thing that we're multiplying. Because the number of significant figures in the result needs to equal the number of the least precise measurement used in the calculation. So what do I mean by this? Well, if I have 6.38 times 2.0, and I'm trying to get the answer here, when I put this math into my calculator, I get 12.76. But that's too many digits. So what you look at if you're multiplying and dividing is you need to determine how many significant figures are in each number. There are 3 significant figures here, and there are 2 significant figures here. Your answer needs to match, right, that 2 significant figures. It doesn't. There are 4 significant figures. So what you need to do is you need to round to 2 significant figures, so it will match the least amount. So when we do this, we look at that 7 and we say, hey, that's greater than 5, so our answer needs to be 13. You can also do this with division. So for example, if we have 16.84 and we divide by 2.54, right? And we put that in our calculator, our answer is 6.6299. We look here and we have 4 significant figures. We look here and we have 3 significant figures. Our answer needs to match the lowest number of significant figures, which is 3. So these need to be the 3 digits we have. We look here, that is a 9. So that means we need to round up the 3 that's in front of it. So that would be 6.63. So these are the rules that we follow in multiplication and division. Let's look at the rules for addition and subtraction. In addition and subtraction, the number of significant figures in the result depends on the number of decimal places in the least accurate measurement. Well, what do I mean by that? Let's look here. We've got 11.934 and we're adding 6.8. Okay. My suggestion would be to draw a line to the right of the numbers where the 2 numbers have the decimal place in agreement. So that would be right here. Okay. Your answer cannot be more specific than right here to the 10th place. This line can help you remember that. So when we do this math, we get 18.734. We need to keep these numbers here, so we look at this number for rounding. Because that number is 4 or lower, we stay and our answer should be 18.7. So we are using the number of decimal places there. Look at this example. We've got 37.657 minus 2.1. When we do this, right, I draw my line to the right side of the last decimal place that the 2 numbers have in common. I go through and I do this math and I see that it's going to be 35.557. That line helps me remember that these are the ones I need to keep, and I need to look at this for rounding. That's 5 or higher, so we're going to round it to 36.6. We'll do more examples of these in class. If you have any questions, I would be happy to answer them then or within office hours.